Hello, this is Dr. Rogalski, and today we'll be looking at Unit 16, Chapter 16, called Reaction Kinetics. Reaction kinetics is just a fancy way of saying how fast will a chemical reaction go. One thing I'd like to point out is that we will be covering the entire chapter, but not section 16.4, which is on reaction mechanisms. There are a number of online resources. There are several listed here, but there's also a long list of them online in Schoology with additional links in the long distance learning folder as well. In the last unit, we studied something called thermodynamics, and thermodynamics told us whether or not a reaction would go, whether it was spontaneous or not under the conditions that we were using. If you recall that delta G was a key factor in the last unit. Delta G is called Gibbs free energy. And if delta G was less than 0, we would have a spontaneous process or reaction. If it was greater than 0, then the reaction would be non-spontaneous, and if delta G were equal to 0, then the process would be at something called equilibrium. So thermodynamics told us whether or not a reaction would go. Kinetics tells us how fast a reaction will occur. One thing I'd like to point out here at this point is that reactions can go in a forward or reverse direction, and if they can do either, then they are said to be reversible. And we haven't talked much about this yet, but when we have a reversible reaction, we'll write it using a double arrow. So kinetics, again, is how fast will a reaction go. In our own life experience, we know that rusting, so the process by which rusting occurs, where iron and oxygen react together, is a pretty slow process. If we had to sit there and watch it, we would definitely say that it is slow. On the other hand, when we watch the ethanol combining with oxygen in a combustion reaction, we would think that combustion reactions tended to be fast, at least in our own eyes. There are reactions that go much slower than rusting, and there are reactions that go much, much faster than combustion. Years back, a Nobel Prize was won for somebody who studied femtosecond chemistry. That was reactions that occurred in 1 × 10⁻⁻15 of a second. So reactions can be very, very fast. So when we are watching reaction rates, or what we call kinetics, we can watch the rate of the disappearance of the reactant or the rate of appearance of the product. In other words, what we're doing is we're watching the change in concentration. We've talked about concentration a couple units ago. Concentration. Okay, these are always running out of space. So we're watching the change in concentration, and that can be of reactants or of products. In the case of this picture here, of the reactant molecules, they are all purple. And so we start off with all reactant, And as time goes along, we convert more and more of the purple reactant into the green product. So at the end of this time, we have the product, and in this case, the product is the green molecules, and the reactants are the purple molecules. So we're watching the change in the disappearance of purple and the change in the appearance of the green. Now there are a number of factors that influence the rate of reaction. And so when we look at the factors that could be important, we have to take a close look at the nature, the chemical nature of the reactants. And so 4 of the important factors that we have, and these are some things that you should memorize. So you want to memorize these, and you should understand them as well. First, the concentration of the reactant molecules. Molecules must actually collide or come together in order for a reaction to occur. And the more molecules you have, or the higher concentration you have, the more likely those collisions will take place. So the physical state is important, and if you realize that the molecules must mix together in order to collide, then things like the surface area and the concentration are important. And we'll talk a little bit more about the physical state in a few slides. The temperature is also a very important factor in reaction rate. Molecules must collide with enough energy in order to react. So you may have a collision, but certain things have to happen in order for the collision to be called a productive collision, and that requires certain bonds to be broken. And in order to break bonds, you know that energy is required. So temperature is another important factor. As I mentioned here, breaking bonds of the reactants, the whole process of a chemical reaction involves breaking the bonds of the reactants, rearranging the atoms, and reforming the bonds to make the products. So that's on a very simplistic level, that's what's taking place in a chemical reaction. Finally, the presence of a catalyst, and you've seen catalyst in biology. Catalyst lowers the activation energy and therefore speeds up the reaction. Okay, so we're going to take a little bit of a look at the reaction rate. How fast a chemical reaction occurs depends on what is happening with the bonds and the atoms in the reactants as they become products. If the process simply involves a transfer of an electron, for instance, if we had sodium plus chlorine, and all we needed to do was transfer an electron from sodium to chlorine. So the transfer of an electron could occur quickly. We're not breaking bonds or not reforming bonds, just a simple transfer of an electron. So we might imagine that that could happen quickly. We have ions and molecules needing to collide in order to react. And when those molecules or ions collide, there's something called an activated complex that is formed, and that is a situation where the two reactants are perfectly positioned, have enough energy in order to move ahead and become product. The energy that's required to form this activated complex, so once you have an activated complex, it also needs to have enough energy to break the appropriate bonds and then move along to become product. That energy is referred to as the activation energy, and we will take a look at that shortly. Why do you think we have this, and why is this energy needed? Well, if we're breaking some bonds in the reactants, it takes energy. Energy is needed always. Energy is always needed to break bonds. And so, and you'll see again, hopefully, that the activation energy is an important part of a chemical reaction. Okay, so here's a picture of ozone. So we have O3, which is ozone. And we have NO, which is nitrogen monoxide. And obviously they're both gases. Those two come together. Those two reactants come together. So these are both our reactants. They come together to form oxygen. So we have oxygen, and we have NO2, which is nitrogen dioxide. And those will become our products. So, in order for this reaction to take place, the ozone and the nitrogen monoxide must collide. They must collide with two things. They must have the sufficient activation energy in order to form the activated complex, and they also must collide with what we say is the correct orientation. Okay, so if we look at the pictures, we see that we have two colliding here. We have, this is our NO right here. This is our ozone right there. And we have an NO bond. This could form, and that would make NO2. And this would be the ozone, or the oxygen, I'm sorry, that would shoot out of the ozone to make O2. Well, this particular picture does have a proper orientation, but it does not have enough energy. So this leads to no reaction. Over here, we don't quite have the correct orientation, or we don't have this doesn't look like quite the correct orientation. We definitely don't have enough energy. So again, this is also no reaction. And then finally, if we actually look at the perfect collision, we have a situation where this NO bond is going to be formed. This OO bond is going to break, so then the oxygen shoots off there. And then this is our NO2, which forms. And this yellow is the energy that was necessary to break this bond, and then allowing the electrons then to form this new bond, and then these two split apart and become products. So that's what we call collision theory. So that it does have a name, so it's collision theory, and it's a pretty common idea in chemistry. Okay, so two things that must occur when you have a collision in order for a reaction to take place. You must have the activation energy necessary, and you must have the correct orientation. Okay, so concentration and reaction rate. We said that in order for reactions to take place, you must have collisions. And it goes It just makes sense that if you have a higher concentration of the reactants, then you will have more collisions. So the higher the number of particles of the reactants, it increases the number of collisions and increases the chance of having a productive or effective collision. Another term that's used is productive. Now, there are a number of ways of doing this. In a solution, you can increase the concentration, or what we call the molarity. So this would be for solutions. But if you're talking about gases, then you would be increasing the pressure of a gas. The higher the pressure, the more molecules of that gas are available for reaction. And if you're talking about a solid, you can increase the surface area of a solid by grinding it up and making it into a very fine powder. When I normally do the thermite reaction, we are reacting rust, iron oxide, with aluminum powder. And both of these are fine powders like baby powder. So these are very fine powders. And that allows for good mixing and a really effective reaction rate, really good transfer of the electrons, which is what's happening in the thermite reaction. Okay, another factor that's important is the presence or absence of a catalyst. A catalyst works in a very specific way. You've seen catalysts before in biology class, and you may have heard of catalyst, and maybe even in your car's engine, possibly. We'll look at that in a minute. Each catalyst has its own specific way of functioning. It depends on the phase of the reactants. And if it's biological, then it's usually called an enzyme. And the key to a catalyst is that it gives a different path for the reactants to become products. And it's, in other words, it has its own reaction mechanism. And the reaction mechanism is basically a series of steps or instructions for how reactants will become products. We won't be looking at reaction mechanisms in 16.4. It's a little beyond the scope of the class, but you'll probably see it later on in college chemistry or AP chemistry if you take those courses. Okay, so how does a catalyst function? It lowers the energy of activation, so it lowers that activation energy we have. And if you're working at a certain temperature, what'll happen then is that you're more likely upon a collision to have a collision that has the energy needed to get over the activation barrier, as opposed to a reaction without a catalyst, which would have a higher requirement for the activation energy. Lowering the activation energy, again, increases what we call the rate constant, K. You'll see that later. And in doing so, it increases the rate of the reaction. And an important note for reactions that are reversible, which we said are reactions that can go forward and reverse. Catalyst increases the rate of the forward and the reverse reaction because it is lowering the activation in both directions. So it lowers activation energy in both directions. One very important thing to realize about catalyst is that a catalyst gets you to the products or yields the products more quickly, but does not yield more product than you would get in an uncatalyzed reaction. So by using a catalyst, you'll get your products in less time, but you won't get more products. So that's an important that's something that's important to remember. Again, catalyst lowers the activation energy because it's providing a different mechanism, which means it's a different pathway, different steps it's taking to go from reactant to product. And then a final important idea behind catalysts is they are not used up in the reaction. So they are present at the beginning of a reaction and the end. So they are present, they do their job, and they remain at the end of a reaction. Now this should look a little familiar to you. It's an energy diagram. So we have the energy on the y-axis and either reaction progress, or we can also think of it as time, on the x-axis. And first we'll take a look at the uncatalyzed reaction. So the uncatalyzed reaction, so we start here at the reactants. We end up at the very top. We have collisions of the two reactants, and we call this the transition state, or it's also called the activated complex. They're pretty interchangeable terms. Activated complex or transition state. Well, once it gets up there, we said it needs to have enough energy so that the transition state can proceed to become products. And that, and also, so at this activated complex, in order for this to actually occur, we need activation energy and we need the correct orientation. And so we do need the activation energy, and if you look at the plot, the activation energy goes right from here all the way up to here. So this is the amount of activation energy that's required such that this transition state or this collision will proceed all the way down to product. So at this point we need some amount of energy to break the necessary bonds in order for the reaction to move ahead to product. So what happens then is if we add a catalyst, the catalyst lowers the energy. So if you look at this, we've added the purple line represents the catalyzed line. And we have this is our first transition state or activated complex. A little later on we may have a second. The first one, however, is if you notice, is much lower in energy than the uncatalyzed one. So this is the activation energy for a catalyzed reaction, and it's much lower. And again, because the reaction is going to take a different pathway. It ends up, in this case, it's showing two humps and these two humps basically represent two different steps. So the two humps represent two steps in this new pathway that the catalyst is providing. Okay, so it's not necessary for you to know what they are. Just be aware that it does lower the activation energy. One other point about the catalyst is that if you look at the activation energy in the reverse reaction, so in other words, we're going back from products to reactants, so we're going this way. Initially, in an uncatalyzed reaction, this is the activation energy for the reverse reaction. And if we have a catalyzed system, then this is the activation energy for the reverse system. So a catalyst affects the activation energy required in both the forward and reverse directions. So this is an example of the Haber process. It's used to manufacture ammonia, which is then used to manufacture potassium nitrates, which ultimately give us fertilizer. So it's a very important reaction, and therefore having a faster way to make it is important. So if you came up with a way of doing that, you would make a lot of money. So the overall reaction for the Haber process is nitrogen plus 3 moles of hydrogen gas. So we're mixing nitrogen and hydrogen gas, and they produce 2 moles of ammonia gas. So imagine what you have then is a big tank. So we have a big tank, and we have nitrogen gas and hydrogen gas bouncing around inside the tank. And now these molecules must collide. So we need 3 of the hydrogen molecules to collide with one of the nitrogen molecules, and we need the nitrogen and hydrogen bonds to break, and then we also need the nitrogen-hydrogen bonds to reform. So if you imagine then, what are the chances of these molecules all coming together in the right orientation with the right energy in the gaseous form to actually have ammonia formed? So it's, the probability is not great. So if we add a catalyst, and in this case, basically, this is a metal catalyst. The metal catalyst is made out of iron, aluminum oxide, and potassium oxide here. What it does then is it attracts the gases. So the catalyst attracts the gases, the N2 and the H2. And if you look at this, it actually has broken up the bonds as well. So it kind of breaks up the bonds. So now what has to happen then? So this catalyst has provided a place for the gases to land, for those bonds to break. And then it gives it a chance for these new bonds to form. And after the new bonds are formed, so this is NH3, and this is also NH3. So when these new bonds form, these new NH bonds form on the catalyst, you can make it so that you can remove this, and now you've got ammonia, and it's taken place with less energy because everything's kind of brought together. Okay, so that is the Haber process, and a very important manufacturing process for fertilizers in agriculture. Okay, one that might be a little more familiar to you is something called a catalytic converter in your car. What you have happening then in your catalytic converter, you have your combustion. Your combustion reaction is taking place inside your engine, and what comes out of your exhaust would be things like CO, it's CO, carbon monoxide, plus other unburned hydrocarbons, nitrogen monoxide, nitrogen dioxide. There can be also SO2, and the catalytic converter, which is usually made of platinum or rhodium, platinum, palladium, or rhodium. They're all metals. If you have to replace the catalytic converter, it's kind of expensive, but these metals allow us to convert something like carbon monoxide into carbon dioxide. Carbon monoxide is a deadly gas if you were to inhale it, because it binds to your hemoglobin and would block oxygen to your blood. And then the NO and the NO2, SO2 is converted to nitrogen and oxygen. So it's much better to have nitrogen and oxygen released into the atmosphere than NO or NO2. These, when combined with water, can produce acid, so could contribute to such things as acid rain. So it's helpful to decrease the amount of what are called NOx and SOx gases. Any of you taken APES this year should be familiar with those terms. Okay, and finally, one of the catalysts that you should have heard about in biology, and I'm sure you have, is called enzyme catalysis. And they refer to this as the lock and key mechanism. And basically, it is a pretty amazing process. You have something called a substrate, and you have your enzyme. Your enzyme is an incredibly complex and amazing molecule held specific in a very specific way. If you look at this, this is your substrate that's going in there, and some kind of chemistry needs to be done on it. And you have this amazing enzyme, this active site, and the entire very amazing shape of this enzyme is created using intermolecular forces. So this enzyme is held together using things like hydrogen bonding, LDFs, so it creates hydrophobic or hydrophilic regions, and even dipoles. So this all ties back to something we've seen before. Once this substrate enters this region, the chemistry will happen, whatever it is that needs to be done, and you'll see it here. This maybe some part of this molecule has to be broken apart, and so then your products are formed, and your enzyme remains intact. So this is a extremely simplified version of what happens, but without these enzymes, nobody would be alive. All right, that's a good start on kinetics, or the rates of chemical reactions. That's a more qualitative look to this point. After this, we're going to start taking a more quantitative look at chemical reactions, or kinetics, the rate of chemical reactions. Time will remain. Okay, so we're going to take a more quantitative look at this, and I'm going to show it to you first in words, and then we will translate into numbers. So back to a balanced equation. When a chemical reaction is taking place, the moles are going to be consumed or used up and produced. the products will be produced at rates based on the balanced numbers in the equation, the stoichiometric coefficients. So moles are consumed and produced at rates based on the stoichiometric coefficients. Okay, so the stoichiometry is important again. You're probably noticing how chemistry continues to build on itself. Stoichiometric coefficients. Okay, the rate expression is going to be an equation that shows how experimentally each reactant or product changes. Okay, experimentally is key here. All of this work is going to have to be done in a lab. We're obviously not going to be doing that, but it does describe how the reactants go down and the products are produced. And the rate law, the way we write the rate law is to see how the rate changes as you vary the concentrations of the reactants. So we have something called the rate expression. We have something called the rate law. We have something called the rate constant. So all of these three parts are going to be combined to describe the reaction of reactants to produce products. The rate law includes something called the rate constant. This rate constant we call with this we rate with a small k. And the units of the rate constant vary, and we will learn a way to figure them out. So we have rate expression, rate law, and rate constant. And the best way to go about learning these things is to actually just practice. Okay, so like I said, rate laws are always determined experimentally. That means do experiments, collect data, and it's always going to be in terms of the concentrations of the reactant. So when we rate the rate law, we're always going to be looking at reactant concentrations. Okay. And finally, the order, this is a new term we're going to learn about. The order of a reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. So this is something to pay attention to. It's a place where if you're not really thinking about it, you could forget and use the coefficients of a balanced equation and call them the orders of the reaction, and that's not the case. And the whole term order is something we're going to be looking at very soon. Here we have some reactants, and we have products, and the rate law is going to be, so this was F2, and this is ClO2. And so the rate, we'll say the rate is equal to our rate constant. And then we're looking at the change in concentration, in this case the decrease in the concentration of the reactants. This reactant is fluorine, and this reactant is ClO2. So we are watching them decrease. And you'll notice there's a number here, and there is actually a number, there would be a number 1 there as well. And these are called the order of F2 and ClO2. Okay, and all they're simply doing in this example is saying, okay, the order with respect to ClO2 is 1, and if you go back to the balanced equation, the stoichiometric coefficient is 2, therefore order does not equal stoichiometric coefficient. So order is not the stoichiometric coefficient. So now let's take a look at the rate law. The rate law expresses, again, the relationship of the rate of a reaction to the rate constant, and the concentrations of the reactants raised to some powers. And those powers are what we just called orders. So if you take a look, this is the rate of my reaction. It is equal to the, so this is the rate of the reaction. It is equal to K, the rate constant, times the concentration of A. It would be in molar, or it could be in atmospheres or some other unit for pressure, to the X. So X is the order of the reaction with respect to A, and then we have the other reactant B, and Y is the order with respect to reactant B. And if you take the sum of the two orders, you'll have the overall reaction order. Okay, so this is some stuff you just have to basically memorize, so it's not hard. Reactant A, reactant B produces reactants or product C and product D. The rate law is the rate, which will be some kind of change in concentration over time, is equal to K, again the rate constant, times the concentration of A to the X order, times the concentration of B to the Y order. Now, X and Y must be determined experimentally. So that means we have to run many experiments and collect data. So briefly going back over this again, we have the rate of a chemical reaction. That'll be some change in concentration with respect to time. We have the rate constant K. Again, rate constant will be figured out from the data, times the concentration of the reactant A to the X power times B, concentration of B, again, molarity, or in the case of a gas, some unit of gas pressure. So B to the Y order, again, X and Y have to be determined experimentally. Okay, so let's begin writing the rate law for the reaction of fluorine gas with 2 moles of ClO2 to produce 2 moles of FClO2. Okay, so let's just start by writing the word rate equals K, our rate constant, times the reactant fluorine to the power X. These orders or these exponents can be anything. You can call them M and N, or A and B, or X and Y. Different textbooks use different things. It doesn't matter. So the reactant fluorine to the X order times the reactant ClO2 to the Y order. So that's just a generic way of laying out the rate law for this reaction. Now, what we need to do is to experimentally determine the value for X and the value for Y by looking at the data chart that's been provided. When we want to find the value for X, we hold, so I'm going to write this down. When we want to find the value for X, we're going to keep, so look for X. We will, when we're calculating X, we're going to keep the concentration of ClO2 constant. So we only want to see how changing fluorine affects X. So in doing this, if we take a look at the data, we're looking for X, which means we're looking for where F2 changes, but ClO2 is constant. So if you look at the data chart, we have ClO2 is constant in experiment 3 and experiment 1. And if we look at the concentration of fluorine, we can see that it is changing. In fact, it's doubling. So we are going to choose experiments 1 and 3 to determine X. So we choose experiments 1 and 3, and we will set up an expression there to determine how X, or how the fluorine changes the rate when ClO2 is constant. Now, when we are going to be looking for Y, we will be keeping F2 constant and seeing what the effects are on the rate when we change the concentrations of ClO2. So if we're looking for when F2 is constant, but ClO2 is changing, then we're going to choose experiments 2 and 1. Okay, so now the slide does show some really a quick sort of eyeball method that you could use, but usually you need to show more work, and so we're going to do the work on the next slide. Everybody hears that, you know. I'm gonna get bad YouTube ratings.
Your teaching will make up for it.
What?
What the hell's that noise?
I don't know.
That's gonna get you bad YouTube ratings.
Oh, shoot. Okay, now in looking for the order with respect to ClO2, so in other words, Y, we said we would choose 1 and 2. So we're going to put rate 2 over rate 1 equals rate 2 is 4.8 times 10 to the minus 3 over 1, which is 1.2 times 10 to the minus 3 equals point. So rate 2 again. The concentration then is 0.04. So 0.0.040, 0.010 to the Y. So if you go ahead now, this is 4. So 4 equals, and this is 4 right here. This is a 4. This is 4 to the Y. Therefore, Y equals 1. So this is the order. And when we write the word with respect to, you can abbreviate it with WRT, and that'll be ClO2. Okay, so now we have the orders of the reactions with respect to each of the reactants. So now we will write rate, and this will be the rate law. This is the expression. So rate equals K, the rate constant, times the concentration of F2 to the 1, ClO2 to the 1. And the truth is you don't really have to write the ones, so writing the ones is not necessary. They're understood. If it helps you think about it more clearly, then you can go ahead and write them. And then finally, if we were to ask what is the overall order of the reaction, so the overall order is equal to the sum of the orders for each reactant, then it would be equal to 2. It would be 1 plus 1. Okay, so this is, we're part of the way to writing the rate law, and we'll practice this first for a while. The rate law eventually will require us to solve for the value of K and then substitute everything back in. So this is the first part of the quantitative type of problems that we'll be doing in this unit. And in fact, this is really about half of it. So there's not a lot of quantitative kinds of problems in this is in the way that there was in the thermal unit. Okay, so we'll take another look at writing the rate law from experimental data. The equation this time is the reaction between oxygen gas and nitrogen monoxide to produce nitrogen dioxide. So writing a generic rate law for this, we would say, okay, rate equals K times the one reactant, oxygen, and in this case they use M, could be X, doesn't matter. So oxygen to the M order and nitrogen, the other reactant, to the N order. So M and N could easily be X and Y, doesn't matter. Okay, so when we are doing these kind of rate laws, we are actually using the method, a method called the method of initial rates. That's not such a big deal, but if you see the title here, it says the initial rates. And this is called the method of initial rates. And we use, and what the method of initial rates means is that we're going to analyze the concentrations of the reactants only in the very beginning of the reaction. So method of initial rate says we measure the concentrations of, in this case, O2 and NO early in the reaction before the concentrations have changed significantly. So if you're only looking at these things early on in the reaction, the concentrations won't have changed much, because remember, in order to have a reaction or a reaction rate, you must have collisions between reactants. And if you wait a long time, you're going to have much fewer collisions because your reactants will have already turned into product. So we use this thing called the method of initial rates in order to determine the rate law. So in this problem, obviously we are going to have to find the values for, we'll just go with their variables M and N. And here are the concentrations of the oxygen. Here are the concentrations of NO. And these are the initial rates. And as you can see, it's molar per second. Okay, so what we're going to do is go through, work this through one part at a time. The textbook actually has some of it already worked out, I believe, in the next slide. So yes, in this slide, they've already shown you how they have worked out at least the value of M. We will... Okay, so in this case then, they have figured out the value of M, and right here. And we'll do the calculation for N on the next slide, but let's go through this. If we want to find the order of the reaction with respect to oxygen, or find M, then we need to find experiments. So we're going to find experiments where O2 varies and NO is constant. Okay, so we have to go back to the data table on the previous slide, and what we would do is look for the data where we have held NO constant. So that actually looks like experiments 1 and 2, and also where oxygen is varying. Okay, so we can choose, and I would always suggest that you write this. Choose experiments 1 and 2. Okay, that you've thought about it, you've decided which sets of data you're going to use, write it down. Okay, and again, put the larger rate on top. This will make your math easier. Okay, math easier. Okay, and now they've actually written the whole thing out, so this is a good one to take a look at. This shows you where it's actually coming from. They actually take the entire rate expression for this particular reaction, and they wrote it here and here. So again, this is going to be, and if you take a look at this, you find out the K's will cancel. K's are canceling. You find out what's being held constant is canceling. And all you're left with is the ratio of the oxygens, which is right here. And then you're going to have the ratio of the rates. Again, the larger one's on top, so that makes it easier. And that comes down to, so if you look at units, the time units will cancel. You'll end up with this value, which becomes 2. If you look at the change in the oxygen values, then you see that it's also 2. So if you look at these numbers here, right here, these are the oxygen values. That's 2 to the m. This is actually this 2 right here. And that's this 2 right here. So 2 equals 2 to the m, or m equals 1. So now we know that m is equal to 1. We have to do the same thing for the other reactant, which is nitrogen monoxide. And we'll do this from scratch on the next slide. So we're looking for N. And that means we need to change the concentration of nitrogen monoxide and hold O2 constant. If you look at the data table, then we're going to choose experiments 1 and 3. And we're not going to rate the whole the ratio of the rate laws out completely, but we'll rate the rate. So we have 12.8 times 10 to the minus 3, again, molar per second, over 3.21 times 10 to the minus 3 molar per second, equal to 2.60 times 10 to the minus 2. That's the concentration, 1.3 times 10 to the minus 2. So molar. And that will be to the N. So if you take a look at this, this comes out to be 4. This comes out to be 2. So 4 equals 2 to the N, or N equal 2. So this then is something a little different. The other values were all 1. So this means this is, the reaction is, we'll write it out, reaction is, if it's a 2, we call it second order with respect to NO. In the first page, or the first calculation, we found out that M was equal to 1, and we would say that the reaction is first order and WRT with respect to oxygen. And then we would be, if we were asked the overall order of the reaction, the overall order of the reaction would be the sum of the two. So overall order of reaction equals 2 plus 1 equals 3. So the overall order of the reaction is equal to 3. Okay, just to continue this, what we'll do now is write the rate law. So we're going to write the rate law expression. Don't get too worried about the term rate law expression. Not that important. So the rate law expression for what we have right now is the rate equals K, my rate constant, times oxygen, and oxygen was first order, times the concentration of nitrogen monoxide, which was second order. Now we have one more thing to do to actually complete the process, and that is to find the value of K. So we need to find K. Now we can find K by going back to the data table and picking an experiment. I always say pick the first experiment and substitute the data back into your rate law. So let's go back to the data table. So go back to data table. Choose an experiment. I always say choose the first experiment. And sub in all the data. And it's important to use units too. With units. Okay. So if we pick the first experiment, let's write the rate law. So we have the rate law up here. So we have rate equals K O2 NO2. Go to the first experiment, go back and substitute in, let's pick the first experiment. The rate is equal to 3.21 times 10 to the minus 3. Units for rate is always molar per second, equal to K, my rate constant. The value for O2 in the first experiment was 1.10 times 10 to the minus 2 molar. The concentration for NO was 1.30 times 10 to the minus 2 molar. And this is, we have a 2 here, so we're going to put a 2 here. And now we have all of our values substituted into the equation. We're looking to find K, so we're going to solve for K. And K comes out to be 3.21 times 10 to the minus 3 molar per second. Keep your units. Divided by 1.10 times 10 to the minus 2 molar. Divided by 1 times 1.30 times 10 to the minus 2 molar squared. And now you go ahead and you do the math, and the answer comes out to be, don't forget the squared term, 1.73 times 10 to the 3. That's the value. Now you have to figure out the units. This is the rate constant units is kind of a big deal. And so we're going to just look at the units. We're focused on the units. So let's write them out. So we know K is equal to molar per second. So here's molar per second. This is molar per second. Here's molar per second. And we have molar on the bottom here, right here. This is molar. Here's molar. And then we have molar squared. So we have another 2 m's. Now what you want to do is cancel everything out that you can. So molar and molar cancel. And so in the end, so we'll add another slide. Let's just go back. So in the end, we'll write it over in the other corner here. We have the units for the rate constant equal to 1 over, remember, because everything's on the bottom, SM squared. And a way to write this would be S to the minus 1, so it's equal to S to the minus 1, M to the minus 2. So these would be the units for the rate constant for this reaction. Okay, so that's the whole thing. There are quite a few steps. It looks like a lot, but we will practice it, and you'll get pretty good at it. So this is the whole thing right now. So if you can understand this, you'll be in great shape. Oops. Okay, so here's another example of one of the gaseous reactions that occur in a car engine. And so we have the reaction between nitrogen dioxide and carbon monoxide, producing nitrogen monoxide and carbon dioxide. And so we kind of generically write the rate law. Rate is equal to the rate constant times the concentration of NO2 and the concentration of carbon monoxide. And in this case, they're using M and N as their variables. You are provided the data, a data table, and again, just notice they're telling you these are initial rates. These are also the initial concentration, so we're using the method of initial rates. And the question asked for us to rate the rate law. So we have to solve for the order with respect to each reactant, and using the method that I just showed you, we'll end up, this is my generic rate law, we'll find M and N, we'll substitute that in, we'll have the rate law, then we sub in one complete experiment to find the rate constant K, and then we'll have the entire reaction. So first, if we're looking for NO2, we're going to choose 2 experiments in which carbon monoxide remains constant and the NO2 varies. Now, the solution for this is on the next slide. I think that everything's laid out there. So we'll go through it ourselves in detail. But as you can see, in looking for the experiments to find the order with respect to the M value, which is the order with respect to NO2, we looked for where the NO2 was changing and the CO was constant. So again, we would say choose experiments 1 and 2, and we're going to put larger number on top. So in picking those numbers, we pick experiments 1 and 2. 2 goes on top, so we have these numbers here. So the rate for number 2 is 0.080, rate for 1 is 0.005, concentration for 2 is 0.040, for NO was 0.40, and for rate 2, and then 0.10 for rate 1 to the M. So 0.08 over 0.005 gives us 16. This ratio gives you the 4. So 16 is equal to 4 to the M, and M would be equal to 2. And then we would say in words, the reaction is second order in NO2, or with respect to NO2. Okay, so likewise, to find the order with respect to carbon monoxide, we would choose, and we're looking for experiments where NO is constant and NO2 is constant and carbon monoxide is changing. So in this case, we would choose experiments 1 and 3. So the same kind of setup here. You'd end up again with, this is your rate data. So this is from experiment 1. I'm sorry, this is from experiment 3. This is experiment 1. These are the concentrations for carbon monoxide right here. And what you end up with is 1 is equal to 2 to the N. And in that case, then N must be equal 0. And so that is the way we'd say it in words, is the reaction is 0 with respect to carbon monoxide. So what that means is that CO has no effect on the rate of reaction, some RXN reaction. So in this case, carbon monoxide doesn't play any role in how fast this reaction will go. So if we go back to our standard rate law expression, we will have the rate equals K times NO2 to the second order times CO to the 0 order, and anything to the 0 order is 1. So we end up with rate equals K times NO2, nitrogen dioxide squared. And that's it for that problem. If you wanted to write out the complete rate law, you would basically solve for K and sub in data. So you could pick any experiment. I always pick the first to save time. Sub in the data, and you would find the value for K, just like we did in the last experiment. Okay, what we'll actually do is go ahead and calculate the rest of the rate law, and we'll determine the value of the rate constant. So we have this, we have rate equals K NO2 squared CO to the 0. So we know that this is going to be 1. So we're going to find K equals the rate divided by NO2 squared. Now, I'm just going to pick data from experiment number 1 and substitute in. So the initial rate for experiment number 1 is 0.0050, and that's always molar per second. And the concentration of NO2 for this experiment was 0.10, and of course that's squared. And now we'll find the value. So I have to do a bit of a calculation here. 50. Can take a minute and do that yourself. Okay, so 0.10 squared gives us 0.01. K equals so K is going to be equal to 0.0050, 0.01, comes out to be 0.5, and let's see. Looks like 1 sig fig will work. And now the important thing with the rate constant are the units. So let's lay the units out. We have up here molar per second. Right here, there's molar per second in rate. And then we have 0.10 molar squared. So we have a molar and another molar. So we cancel out the molars, and that comes out to be 1 over SM, or the way we'd write this is 0.5 S to the minus 1, M to the minus 1. So that would be the value of the rate constant for that reaction we just figured out. And if you wanted to write the entire, rate law out, you would write rate equals 0.5 S minus 1, M minus 1 times, these are brackets, times NO2 squared. And now, given this, you could get any set of data, and off any set of experimental data, substitute in the concentration for NO2, you know the rate constant, and you can calculate the rate of the reaction. Okay, so that's another one of those examples of the whole thing. All right. So this is, yeah, another one of the rate law calculations or determinations. It asks to find the orders of the reaction. So in this process, you're going to need to rate the generic rate law. So we have thiosulfate, and we have iodide. So they come from right here. Notice we're not paying any attention to the stoichiometric coefficients. We're finding the orders from experimental data. So orders from experimental data. So we have to find the orders X and Y. Once you find the orders X and Y, then you come down here. So again, they've eyeballed it. You can do all the calculations in the same way we've been doing it. And what you want to do then is find the value of K. So once you've determined the rate law, then you solve for K, substitute in all your data, pick one experiment, substitute in all the data, and find the value of K. So this is the same thing. All the math hasn't been shown, so it does say if you double I minus, the rate doubles, so that means it must be first order. The same thing with thiosulfate. If you double that, the rate doubles, so that again must be first order. And so they're not written here, but we can see that they are first, they're both first order. Okay, so that's it for this problem. Okay, on this slide, we will practice some more word-like experiments, but they have to do with reaction orders. This comes from the THQ on Kinetics. And they're giving us a reaction of O2 plus 2H2 produces 2H2O. And the question says to rate the rate law. So we're going to rate the rate law. Okay, so first one is A. It says the rate is second order with respect to oxygen and third order with respect to hydrogen. So let's write that out. The rate is equal to, always the rate constant. We have oxygen as one reactant, and it claims that it is second order with respect to oxygen, so that makes it a 2. And that it is third order with respect to hydrogen, so that makes this 3. So translating words into an equation is pretty easy, but it can get more tricky. So B on this take-home quiz says that the rate is first order, so rate again equals K, oxygen. The rate is first order with respect to both oxygen and hydrogen. So, sorry, H2. And so they're both first order, so we don't actually have to rate them. It's understood that there's a 1 on each of these. Okay, so that's easy. Now, these are a little harder. Let's think about these. So rate equals K. Okay, C states that the rate is doubled when only the oxygen is doubled. So if the concentration of something is doubled and it causes the rate to double, then we know that's going to be first order. And is doubled and stays the same if only the H2 is changed. So when we change H2 concentration, if we double it or quadruple it, but the rate is unchanged, that means H2 is 0 order. And therefore then, if we're writing the rate law, it's going to be equal to K times O2. Because H2 to the 0 is really a 1. Okay? D. When only H2 is doubled, the rate increases by a factor of 3. When only H2 is doubled, and the rate increases by a factor of 8, so we'll have to think of, well, what exponent gives 2 to the what exponent gives 8. And the rate stays the same if only O2 is changed. So let's just start rate equals K. Oops. K. So the rate stays the same if only O2 is changed. So that means O2 must be to the 0 power, has no effect. And if H2 is doubled, the rate increases by a factor of 8. So that must mean H2 is to the 3rd power, because 2 to the 3 equals 8. Okay, and finally E off of this THQ, rate equals K. When only O2 is doubled, the rate doubles. So if we double one and the other's doubled, that must be first order. And when only H2 is doubled, the rate increases by a factor of 4. So if H2 is doubled and the rate goes up by a factor of 4, 2 to the 2 is equal to 4. So hydrogen must be second order. Okay, so this is another type of problem that you could see. It's more qualitative in a way because there's no actual data that we're using. And these came off of the THQ for Kinetics. Okay, so another kind of problem, this will be the TA off the THQ for Kinetics. And it is number 3. We have a reaction, G plus R goes to Z. And they tell us, so the rate law, K, they tell us that the reaction is second order for G, so that's going to look like that, and first order for R, so that'll have a 1 here. And now they're telling us that G, concentration of G, is 0.0322 molar, and the concentration of R is 0.106 molar. And at these concentrations, the rate is equal to 8.79 times 10 to the minus 6 molar per second. What is the numerical value for K, the rate constant? So part A, we're finding the rate constant. So we know that what we might as well do is solve for K. K is going to be equal to rate divided by G, concentration of G squared divided by R. We just substitute the numbers in. K is equal to the rate, so the rate is given at 8.79 times 10 to the minus 6 molar per second. Divide by G squared, which is Okay, so we lost some of the audio for this. This was THQ Kinetics number 6. And we were given a data chart. There's a data chart. And we were given the rate law, rate equals K times A to the 4th. All we needed to do was simply take the data off the chart, substitute it all in, and we had the final answer of rate equal 3.67 times 10 to the minus 2. Units for rate is always molar per second, unit time. Okay, so the next slide. This is again THQ Kinetics. Number 6, part B, so to speak, or it's finding the concentration of A for trial 2. So we know rate is equal to K times A to the 4th. We know that we're solving for want to find the concentration of A. So A to the 4th is equal to rate divided by K equal to, for trial 2, the rate is 4.75 times 10 to the minus 3 molar per second over K. And K is 6.91 times 10 to the minus 2 per mole per second. And again, that's A to the 4th. And if you take the root of that, don't remember what that's called, you end up with 5.12 times 10 to the minus 1. Concentration must be molar. So that would fill in the blank, the second blank on the chart for concentration of A in trial 2. Okay, so that's actually quite a few practice problems. There are other worksheets that you can look at. There will probably be some other videos that cover some more of these kinds of problems, but this should be quite a lot to work with for now. Okay, I hope this has been useful, and remember there's lots of resources available as well. Thanks.